Hello, welcome back to Learn It from a Layman. I'm Carl. I'm joined again by Matt, Cameron, who's been off for a while, so welcome back, Cameron. Work and all that. Johnny, who is generally put upon to do the podcast when he comes on, but this time Johnny will just get to be one of the crew.
I'm already sleeping.
Which is what Johnny does best when he's not being a doctor. And then Tim, who, well, if you've been listening,
I'm like the crew's sidekick.
Okay, and today we are going to be discussing the subject of terraforming, which for you laymen out there is essentially changing a planet in a particular way, generally to be habitable. And so this is all kind of in the sci-fi realm. None of this is, some of this I'm sure there's grounding in some real work that's being done, but there's no practical terraforming that's been done. All of this is at least hypothetical, if not entirely science fiction based. But let's start a little bit. Johnny was just asking a question right before we got on the podcast. It seemed like a pretty good place to start. Johnny, you were asking something about the atmosphere.
Yeah, so I mean, obviously we get our air that we breathe from the atmosphere. It's very important for life. And the discussion was, well, if we went to Mars, we would need an atmosphere. And so I was saying, well, what keeps our atmosphere around? Is it gravity? Is it something else? I'm just not really sure.
And I was going to let Matt see if he could answer this question.
For those who weren't here for the pre-talk, which was everyone, we kind of organically arrived at this topic. It was a beautiful
organically,
thing.
Organisms.
That's
yeah,
right.
With a carbon backbone, we came to this organically.
That's right.
Yeah. Okay. So there have been different ideas about why we have an atmosphere, and why it hasn't bled away into space. The basic thing is that Earth has gravity. Well, that's a revelation. But yeah, the fact of the Earth's mass means that other mass is attracted to it. And we've talked about the equation for gravitation between different objects. You have mass 1 plus mass 2 times some constant that I forget, divided by the square of the distance between the masses. Well, if your masses are large, then that force becomes pretty large pretty quick. And that's cool. So you may ask, though, how come other planets don't have atmosphere if gravity is all that it takes? Well, they do, just not as, effective at being, a habitable atmosphere. Mars, for example, has it's about a little over 0.3, almost 0.4 times Earth's own gravity. Martian gravity is much weaker. It's about 60% lower than what you have on Earth. Well, that means that you have 60% less force holding air in place. And so there is air. It's just much freer to bleed away out into the vacuum of space. And that leads to other problems like, 1, is there enough air for me to breathe? No. 2, do I have enough air and atmosphere to shield me from all of the radiation that the sun is kicking out that will kill me if I don't have adequate atmospheric protection? The answer to the second question, weirdly enough, seems to be maybe. We sent some probes to Mars, and they found out that radiation levels on Mars were much lower than expected, which is kind of cool. But the problem still remains that I don't really have enough air to breathe, and I don't even know. I have actually no idea on this one. Even if I had a bunch of atmosphere, that doesn't mean but that atmosphere is made up of enough of the elements that humans require to survive, like oxygen, in its composition. You have an atmosphere with, X amount of oxygen, and that is less than what a human needs to survive. Well, you're going to have a less good time, even though technically you have air. Does that make any sense?
I think so.
I guess that from like a medical perspective as well, you see these hikers and people that go up to very high mountains, and they can get pretty sick because the air pressure is a lot lower. Would you run into something like that? Since what is Mars's air pressure, for example, is it so much lower that we just wouldn't, even if they did have the right amount of oxygen, would it just be impossible for us to actually physically breathe it in because the pressure's too low?
I don't know exactly. I would not be surprised at all if that were the case. I'd have to look at Google here, which I'm going to do. But yeah, if humans are kind of delicate creatures. If outside air pressure gets too high, we kind of implode on ourselves. You run into that with deep sea exploration. Submariners run into a disease called the bends, just because even though they're inside a submarine, you get too much pressure down there, and it hurts. The body doesn't respond in a way that a body normally would under normal pressure conditions. So, and the same is true at low pressure. You climb up a mountain, your lungs start to not work the same way. You run into something called hypoxia that's more oxygen deprivation. But the pressure thing is a concern as well. So at
Matt,
ground level on
just
Mars,
interestingly,
yeah, go ahead.
yeah, interestingly, the reason you have oxygen in your blood, there's a couple reasons, but one of them has to do with the partial pressure of the oxygen in the air will diffuse into the blood without the need for like hemoglobin or another carrier to carry the oxygen in the blood. So because you're like up a mountain, you get hypoxia because you just don't have enough pressure of oxygen to get into the blood like you do at like sea level, for example. So
Yeah, no, that makes sense. I was just looking it up. So Earth's air pressure at sea level is 14.7 psi, pounds per square inch. That means that while you're sitting here at 0 feet altitude, you have 14 pounds of air weighing down on every square inch of your body. That's good. It keeps your ears from exploding, and it keeps your guts nicely tucked inside you, and it makes it easy for you to breathe. If you go to Mars and you start sniffing around the Martian atmosphere, you're quickly going to realize that it's not doing the same thing for you. And part of the reason, is because the pressure is much lower. The Martian atmospheric pressure is about 0.095 psi as compared to 14.7 psi. For context, that is like less than 100th of the pressure of Earth. Less than 1%, way less than 1%. So, that's an issue. That if you're running around on Mars, you would require a pressure suit of some sort, like a space suit, in order for your various bodily fluids not to boil away.
that was a fantastic visual.
Thank you. The other thing that was thought for a long time was that because Earth has a magnetic sphere around it, magnetosphere, that magnetosphere holds the atmosphere in place. Well, that was kind of the belief for a while, but then we actually sent some probes to Mars, and we looked at what the how much atmosphere there was floating around up there. And it turned out that there was a surprisingly large amount, more than we thought there would be, more than would have been expected if a magnetosphere is the only thing that keeps your atmosphere in place, because Mars does not have a magnetosphere. The Martian magnetosphere, the Martian magnetic field is such a complicated mess that it's just not a coherent thing.
Okay. So basically, you're saying that Earth has a coherent magnetic field around it, and because of that, that provides a kind of protective bubble from the solar wind, the blasts of radiation that are coming off of the sun. Mars, whatever magnetic force action is going on in the planet, isn't coherent or not really creating a big magnetic bubble, and so the Martian atmosphere is much more prone to get torn away by solar radiation. Am I understanding it right?
Yeah, that was the idea. With Earth, you have a North Pole and a South Pole, and that's good. And it's nice and straightforward. Your South Pole is south, your North Pole is north. If you look at Mars's polarity, it's far, there's poles all over the place. There's not a North Pole and a South Pole. There are just magnetic pockets. The magnetic field lines across Mars just go all over. There's not a coherent magnetic field. Well, that's an issue if you're trying to have a coherent magnetosphere. And so the thought was, because Mars doesn't have that, then it wouldn't be able to have a magnetic field, and therefore it wouldn't be able to hold in an atmosphere that would shield Martian inhabitants from all of that solar radiation that would, kill you. Well, we sent some probes up to Mars, and we found that even though there isn't as much atmosphere, weirdly, there is much less radiation on the surface than we expected. So what does that mean? Well, the radiation is blocked by more than just the magnetic field. And I'm sorry, we're kind of confusing a couple issues. The atmosphere, we know that blocks radiation somehow, to some extent.
So basically, you're saying if I go swimming on Mars, it's probably okay, but I should wear a lot of sunblock.
No.
We've talked a lot about pressure and atmosphere, which are obviously very important in terraforming, but they're not the only considerations, because temperature is also pretty darn important. We don't do very well with extreme temperature fluctuations as humans either. So, and once again, anything outside of, I guess they call it the Goldilocks zone, being a planet around a particular star. Go back and listen to our astronomy podcast if you have more questions about that. But there's a particular area where temperatures are generally believed to be in a range that might be able to support life, depending on all these other factors as well. But temperature issues are significant even within our own solar system. Venus, I was just looking it up. I mean, the temperature on Venus gets to be, what does it say?
Hot.
127 degrees Celsius on the surface.
Yeah.
Yeah, that's a big number for you, Carl. I understand.
Well, it's more the Celsius issue, all right?
So weirdly, the Venetian temperature is driven by kind of an almost opposite atmospheric problem. Venus has, you might say, too much of the wrong atmosphere. Heat is locked in by cloud cover and just can't escape. And so Venus's temperatures are extreme. Mars, you're right, has the opposite problem. Heat has, well, Mars is smaller than Earth. You know that because of the difference in gravity. That also means Mars has a lower thermal mass. That means it's just not going to hold heat the same way. Thermal mass and mass are very much related, but Because Mars is smaller, it's going to hold in less heat unless there's another compounding factor to help with that heat retention. Venus has its ultra thick, heavy atmosphere. Mars doesn't have that. And so, for that and other reasons, I mean, it is farther from the sun, less intense radiation reaches it than on Earth. That can be, that's another factor. But anyway, the upshot is that Mars's temperature is significantly lower than Earth. At maximum, it gets to about 70 degrees Fahrenheit, which is nice. But the average temperature on Mars is about negative 80 Fahrenheit, which is, I mean, that's like Great Lakes region temperatures.
Right.
Okay,
Yeah.
that was a bit of an understatement. That is far colder than any habitable region that you have on Earth.
Right. It only feels like it's that cold when you're up in like northern Michigan or something.
Yeah, and so there's you have to solve the problem of an atmosphere in order to help with the problem of temperature. At the same time, if you get too much atmosphere like Venus has, you can swing the temperature the other way. But yeah, if you don't have enough, you're going to have a very uncomfortable time where climate-controlled shelter becomes essential. You wouldn't be able to survive outdoors for very long, or rather, outdoors without a climate-controlled suit, like a spacesuit or something. We keep coming back to spacesuits being necessary to live on Mars. I don't know that that's going to change anytime soon.
Right. Well, and so that's, I guess, one of the big things about terraforming and why it seems so awesome if we could actually do it is the idea right now of either a colony on Mars or something like that is completely dependent on, us being able to build some type of dome structure or going underground and generally controlling a small, very small area and with a lot of technology. Where if we could figure out solutions to these, these issues with the atmosphere and generally be able to create conditions on a planet such that it just was able to, regulate, to the point where it can sustain life on the surface and liquid water and those things, then all of a sudden the spacesuits are no longer in play and you can actually go and colonize it meaningfully beyond just specific, small, installations of high technology areas where you have to are completely dependent on oxygen systems and water being transported in or recycled or whatever. So so that's the allure of terraforming. Let's see, Cameron or Tim, do you have any input on terraforming?
Yeah, I want to bring up oh, sorry, Cameron, you go first.
No, it's all right, Tim. You go. It's all right.
All right. Well, I wanted to bring up another problem as far as like terraforming, and that would be the getting there part. So flying to Mars would take months, right?
Well, yes. I mean, it's not a quick trip, but it can be as little as couple months, few months.
Okay, but all that time in outside of the Earth's magnetosphere, any traveler would be we would basically need to bring our own like protection from the radiation of space with us. Is that right?
Yeah, it's one of the problems that you run into is creating the transportation that can heft not only the astronaut, but also all of the shielding required to keep the astronaut alive amidst that giant cosmic microwave. Yeah, the ships that are going to carry people to Mars are going to require heavy amounts of shielding. And that means mass, and that means, less that you have available for your payload. Again, this can be done. but it's it's difficult. There's a couple different ways you can get to Mars. You can do what is called a Hohmann transfer, where you line up your orbits neatly and efficiently, and you can use a minimum of fuel to get a large amount of stuff from one orbit to another, from Earth's orbit into Mars orbit, and that's pretty cool. You could, you would be able to move a whole lot of stuff for not a lot of fuel. Problem is, it takes forever, many months, and so you can do, that's okay if you're not dealing with organic astronauts that are going to, die. So if you're firing off a rover or you're firing just a cargo load of materials to Mars, you can do this more efficient, slower orbital transfer. If you have astronauts, you might want them to get there quicker, and so you can do a direct shot. That is faster, but it takes a ton of fuel. The flip side is, if you go slower, then instead of all of that mass of fuel, you require all of that mass of shielding. So there's kind of a trade there. Yeah, getting to Mars is doable because we keep doing it. We just chucked an SUV and a helicopter up there, so you can get things to Mars. But it is a significant effort. And it becomes more significant when you have an organic life form that you would like to actually survive the trip.
And so when you put all this together, the fact that terraforming Mars would require moving huge volumes of, atmospheric stuff to create the atmosphere or water, and then the people themselves, it would be a phenomenally expensive project, right?
Yeah, it wouldn't be cheap, and things are becoming cheaper and more efficient. But yeah, there would be a lot involved. In order to set up, a serious terraforming project in whatever form that takes, this would not be a single mission by any means. This would be a long, concerted, bazillion-dollar effort of multiple launches hauling multiple loads of cargo out to Mars over the course of many months.
Probably, right? But there are different options on how we terraform. At least I'd imagine. I'm no expert.
I'm sure there are, and I don't know what all of them are, what
Well,
the
right,
ideas
so
are, and I don't know what the postulated resources include.
right.
But
I'm
yeah,
because
go ahead.
I could conceive of us essentially coming up with some type of I mean, I call it a bomb for lack of a better word, but something that we just shoot essentially at Mars that on the surface explodes, and inside of it has a lot of a particular element that we are trying to create a particular reaction with. And so we essentially bombard Mars with a bunch of these in order to produce a particular reaction on Mars. Those types of things, while still expensive, would be significantly less expensive, and we don't have to deal with shipping people there until we've done a bunch of things to Mars to the point where we've gotten it, hypothetically at least habitable, right? So we shoot a bunch of hydrogen bombs at Mars, introducing hydrogen, this copious amounts of hydrogen into the atmosphere there to see what kind of reaction it has.
Operation Big Guns.
What you're saying, what we need to do is shoot the Genesis torpedo from Star Trek, whatever it was, into Mars.
I'm telling you, it starts as science fiction, and nobody, sees it as science until it becomes,
So what we need to do is get Spock trapped into the torpedo that we shoot into Mars, and we'll be all hunky dory.
Star Trek was ahead of its time. All right.
That's right.
So I would refrain from making any comment on the actual feasibility of dispensing hydrogen dispensers on Mars and whether or not that would be useful. But yeah, if you have a method of terraforming that involves preconditioning the planet with pre-positioned resources, great, go ahead and do that. But at the end of the day, you're probably looking at finding a way to put a whole lot of mass on Mars. I mean, just the amount of atmosphere that you need. If you think about how much the air around Earth weighs, you don't really think that it weighs anything because it's air. You don't feel it. Well, as I mentioned, though, you have 14 pounds of air pressing down on every square inch of your body all the time. There are you know, there is an unfathomable amount of air around the Earth. That amount of mass, whatever it is, however many, hundreds, thousands, millions, billions of tons, would need to be added to Mars at some point somehow. And just getting that mass there is a thing that needs to be figured out.
I just
we
read
would
one.
have to take the moon and put it into Mars.
Cameron, did you just read that too? Because I just read that.
No, I didn't read that.
You come here to listen to the live Google search results. I'm sorry, you did break up a little bit. What was the thing that you were saying?
Cameron just said that you could throw the moon at Mars. Is that what you said?
Into basically Mars. What Matt's talking, to get that mass, you'd literally have to get a moon in there to increase its mass, which would destroy everything.
Well,
okay.
That would do bad things.
Okay. Well, let's pretend this is a good idea somehow.
I saw this on Despicable Me.
Yeah. So, when you want to move something, there's an equation for that, the kinetic energy equation. Kinetic energy is 1/2 mass times velocity squared. Now, when you're dealing with an orbit, you're dealing, when you want to change an orbit or move something from one orbit to another, you're talking about changing its velocity. Because that velocity term is squared, whenever you change velocity, you're talking about requiring a very large amount of energy. So if you want to take the moon and chuck it into Mars, you need enough velocity, enough energy to affect the moon's velocity. And the moon is not small, the moon is big. That mass velocity squared equation is going to very quickly become
right, but that's
unfathomably large.
That's if you think about us directly hitting something and it, 1-to-1. But if you imagine a chain event, where I was just reading, and yes, I sometimes read Wikipedia during the podcast. Essentially, there's this.
And by sometimes, he means every time.
Every time. Yeah, unless we're talking about the rare thing that we actually know something about, which is not why you turn into this podcast. You turn in to learn things from a layman, which is us.
Okay, Paul Birch, who was a scientist in the UK, was essentially theorized almost what Cameron was saying. Essentially saying, take one of the ice moons, and from the outer solar system, and get it and essentially hit Venus with it. And he said, if you do that, you'd be able. He said, what you'd be theoretically, you would. Anyway, he said you could flick one pebble at an asteroid belt and end up dumping Mars into the sun. So just essentially the idea of chain reaction, gravity, boom, big thing happens as a result. So it would. It's all kinds of calculus involved here, but essentially instead of us having to shoot something directly at the moon or whatever, if you could figure out a way to hit an object enough to change its orbit enough to hit something else, and so on.
Yeah, it's just like darts, right?
Yeah. Okay,
I'm not saying it's
so
easy. Look, I'm not saying it's easy. I'm
yeah,
just saying that
yeah,
there are out-of-the-box ways of thinking of achieving terraforming. That because this scientist also thought, or one of them talked about putting up like solar shades around Venus, essentially projecting a massive um, umbrella, you could imagine, over around Venus to protect it from all of the heat.
yeah. Well, let's think about that. How much solar shade would you need to put up there? What is the weight in pounds per square foot of that shade material? Based on that weight, how much energy do I need to expend to chuck that much mass into an orbit around Venus? Based on that energy requirement and the heating value of my rocket fuel, how much rocket fuel am I going to need to expend? Based on that astronomical number, how on earth am I going to build the billions of rockets necessary to put that much mylar in orbit around another planet to block out the sun? I would suggest that these calculations need to be done before someone throws around the idea of Venetian sun shields.
Okay, well, yeah, the Venetian sun shields, I
That's
don't know.
what
Likewise,
elevator.
using, I'm envisioning what you've described as kind of a celestial pool where you knock one ball into another ball.
Exactly.
Yeah, so that's cool. And if you can line up the balls that are already moving to collide with each other, a small adjustment to one ball could have a large impact on another ball, potentially. Um, but good luck. It's an interesting thought, and there's some significant implications
Oh yeah,
when
I
we
mean, you
talk
could
about trying
seriously
to
mess up
ram
our.
celestial objects into each other. Um,
I
but
just wonder how much, when you're talking about the amount of rocket fuel, I just wonder how many things of Tupperware you would have to fill up to
yeah,
get that much rocket fuel.
well, tune in next time when Learn It from a Layman talks about obscure units of measurement like a bath, and we will talk about how many baths of Tupperware would be required to put up a mylar sun shield sufficient to terraform Venus.
Yeah.
That is
Well,
something that
okay.
I'm going to tune
Now
in
in
for
the
that.
realm of. Okay. Before we wrap up this podcast, as I wanted to comment that we've had lots of people tuning in recently. So thank you. Tell your friends, not about this episode, but about the other ones. Um, No, in
Endorsement.
reality, terraforming is awesome, and I think you've learned something here. And I think we need more resources brought to bear here. But we have, like I said, we have worldwide listener base. We've got people showing up from all 50 states, all the provinces in Canada, all of Australia, and pretty much all of Europe. People all over listening to Learn It from a Layman, so we appreciate that. But for terraforming, let's bring it back to the idea that there's a lot of math to be done here, lots of out of the box thinking, but this would overcome lots of other issues that we'd run into trying to create a particular base on Mars. So while they seem to be planet-sized problems, if they're solvable, they come up with planet-sized solutions. And so,
Let me plug in one thing, Carl, just a kind of a thought as we wrap up. Okay. Even if we, do eventually develop the technology or know-how to overcome these really tricky problems, the expense of doing something like terraforming Mars would be incredible. When I have conversations like this, I like to point out that really we've got a whole lot of area right here in our backyard that could use a bit of terraforming, and we could do a lot cheaper. The Sahara Desert, the outback in Australia, and some of these places in the world that are currently not arable or habitable already enjoy benefits that on Mars are just pipe dreams. They have an atmosphere, proximity to water, the Goldilocks stuff. So it's not near as exciting. But when we think about terraforming and think practically, I think the conversation should always come up to how can we improve the vast stretches of our own planet that are currently dry and barren. And we apply some of these same ideas and stuff. It would be much easier to terraform, the Sahara, for example. So, anyways, just food for thought.
Yeah, because deserts aren't any kind of critical feature of a planet's ecosystem or anything.
Well, in that, right.
And
So,
it would be interesting to take a desolate part of Earth, like Arizona, and test out or prototype some of these terraforming methods on it. Except you can't, because you don't have the same representative environment. You do have an atmosphere. You do have a magnetic field, that which works on Earth. I don't know if you could, with confidence, prove that it would work in one of those other places. But yeah, I'm all for efforts to try to terraform, Arizona and make it a little more habitable to humanity. It's too hot down there.
The old college try.
Yeah.
Oh, and
Now,
speaking of the old
weirdly,
college try,
well, no, I don't even want to go there. I'd get people. No, the
for
Earth is. I should
all
stop
of our
there.
listeners will be interested to know if you would like to get in on the ground floor. We are starting a terraforming fund that you can contribute to, and 100% of funds will go to terraforming something. So get in now.
right, exactly. Yes, our Ponzi scheme.
Tim, you sold that well. You might be able to terraform an ant farm here pretty soon.
Yeah, well, the one thing, so in rebuttal to Tim's idea, well, I think it's true that we need to do more to, yeah, and well, it's far more feasible. These other planets are uninhabited, so if we chuck a bomb at them and it doesn't work out like we thought it was going to.
I really am not sure about hydrogen.
I like these bomb
bombs.
ideas, right?
Bomb Mars. Let's make that some merch. Let's make bumper stickers and T-shirts. Bomb Mars.
Well, there are a number of celestial bodies out there that we could try and experiment on that are more or less naturally, lend themselves to terraforming. Some of the moons of Jupiter might actually be adequate candidates. Titan
those are even
comes
further
up
away.
every now and then. It is farther away. It would require much more energy to get things there.
Yeah.
But, as a proving ground, it might be something that you could use to check things out. But anyway, there's a lot of planets and a lot of planetoids and a lot of things. I'm just glad that we have Earth. Earth is great.
Earth is nice. Okay, and on that note, Johnny, did you have a final word?
Yes. Kids, eat your
And
vegetables.
that was the final word.
Okay. Well,
grow a garden. Make the world a better place. That's all.
There we go.
Right.
Yeah, I think one of the things that comes up in my mind is there's a lot of intelligent people who've kind of sounded an alarm bell about we need to be able to move to another planet because we only have so much time on this Earth and all this other stuff. Okay, I don't know if I agree with that, but what I do think I agree with is that we do have a planet that is pretty awesome. Was custom made just for us. It is incumbent on us all to try to do what we can to not screw the thing up. So I will leave people with that simple thought.
Yes, that is good. So do your best, and in the meantime, learn some terraforming techniques and experiment on Mars. So join us
I'm
next
building
time.
my own hydrogen bomb right now to chuck at Mars.
We do not condone building weapons of mass destruction.
And I'm going to launch it with
I
my
think
own
you condoned it
slingshot.
pretty hard earlier.
Okay. All right. Well, we'll leave terraforming before we get arrested.
And as long as I aim it right, it'll create the correct chain reaction to build a planet that we can all move to.
There we go. That's right. All right.
Yeah.
Like I said, join us next time. We'll be discussing lasers, and we'll see you back then.
I'm sorry, but just that we talk about bombing Mars, and next week's topic, laser. Laser Mars.